Something happened in deep space that NASA engineers are still struggling to explain. Not a malfunction, not a glitch, not cosmic static that can be dismissed with a formula and a footnote. Voyager 1, a spacecraft the size of a small car, built with technology older than the internet, older than the personal computer, older than most people watching this, just did something that broke every model scientists had prepared for. It turned its instruments. It picked up a signal, and then it sent back data that nobody in the room at the Jet Propulsion Laboratory was ready for. Nobody. There's a machine drifting through the darkness right now. It has been drifting for nearly 50 years. It carries no passengers. It carries no weapons. It carries no fuel reserves capable of bringing it back. It left Earth in 1977, the same year Star Wars premiered in theaters, the same year the first personal computers were being soldered together in garages, and it has never stopped moving. Not once. Not for a single second. Right now, as you read these words, it is traveling at 35,000 miles per hour through a region of space so remote, so completely beyond the reach of human experience, that the light from our own sun reaches it only as a faint, distant star among billions of others. That machine is Voyager 1, and what it just discovered is something that even the scientists who built it, who tracked it, who devoted decades of their professional lives to understanding its data, cannot fully explain. Think about what that means. These are not casual observers. These are not journalists speculating from a distance. These are astrophysicists, engineers, mathematicians, people who have spent careers constructing models of the universe based on physics laws tested and confirmed for over a century. And the data coming back from Voyager 1 is making those models look incomplete. Not wrong in a small, correctable way. Incomplete in a way that suggests something enormous is waiting to be understood at the very edge of our solar neighborhood. Something that was always there. Something we were not equipped to detect until a 50-year-old spacecraft running on power levels that can barely keep a refrigerator light on, drifted close enough to sense it. But here is where it gets complicated. Because this story did not begin with a triumphant discovery. It began with silence. It began with months of corrupted signals and confused engineers staring at screens full of garbled data that made no sense. In late 2023, Voyager 1 stopped communicating in any meaningful way. The signals were still arriving, the spacecraft was still transmitting, but the data itself was scrambled, incoherent, like receiving a phone call where you can hear breathing but no words. NASA's team at the Jet Propulsion Laboratory in Pasadena, California, began the painstaking process of diagnosing a problem across 14 billion miles of empty space. And here is the part that most coverage glosses over. A command sent from Earth takes approximately 22 hours to reach Voyager 1. A response takes another 22 hours to return, which means every diagnostic attempt, every adjustment, every test took 2 full days just to produce a result. Imagine debugging a computer problem where every keystroke takes 44 hours to evaluate. That was the reality facing this team. What they eventually found was a corrupted memory chip in the spacecraft's flight data system, the onboard computer responsible for packaging all scientific readings and engineering data before transmitting it back to Earth. A single faulty memory location was contaminating the entire data stream. The fix required engineers to painstakingly reroute the affected code to different, healthier sections of the spacecraft's memory, a process described by mission engineers as the most delicate software surgery ever attempted on a spacecraft that far from Earth. In April 2024, intelligible telemetry began arriving again, and when the science data finally came back online, all 4 of Voyager 1's still functioning instruments, reconnected and transmitting, what scientists found waiting in that data was not what they expected. The universe, it turns out, had not been idle while the engineers were busy fixing the hardware. This is where everything changes. Because the story of Voyager 1 is not simply a story about a brave little machine surviving against the odds. It is a story about what that machine found when it crossed a boundary that no human-made object had ever crossed before. In August 2012, Voyager 1 became the first spacecraft in history to exit the heliosphere, the vast magnetic bubble, generated by the sun's solar wind that surrounds our entire solar system like an invisible force field. When it crossed that boundary, called the heliopause, it entered the interstellar medium, true interstellar space, the space between stars, and what scientists assumed they would find there was more or less emptiness, quiet. A near vacuum of thinly scattered particles drifting in cold silence between one stellar system and the next. What Voyager 1 actually found was something far stranger. The spacecraft's plasma wave system, an instrument designed to detect vibrations and oscillations in electrically charged particles called plasma, began picking up a signal. Not the kind of signal that arrives in bursts when the sun fires off a massive solar flare and the shock wave eventually propagates outward through the heliosphere and into interstellar space. Those events were expected, Those events were already mapped and modeled. This was something different. This was a continuous, persistent, low-frequency hum, narrow in its frequency range, steady, unwavering, and coming not from any single event or source, but from the interstellar medium itself, from the diffuse, near-invisible plasma that threads through the space between stars like an impossibly thin cosmic fog. Cornell University astronomer Stella Koch-Ocker, who led the research team that identified and analyzed this signal, described it precisely and unforgettably. She called it the faint, persistent hum of interstellar gas, and she compared it to the sound of gentle rain after a thunderstorm passes. Read that again. A sound, a hum, not from a star, not from a planet, not from any object or event that physics had previously told us to look for in interstellar space. A hum from the fabric of the space between stars itself, the interstellar medium, a region that most scientific literature described for decades as effectively empty, as a near vacuum barely worth measuring, was humming, continuously, persistently, in a pattern so narrow and consistent that it could not be attributed to random cosmic noise. And Voyager 1 was the only instrument in human history capable of detecting it, because Voyager 1 was the only human-made object that had ever actually been there. But here is where it gets worse, because that discovery, extraordinary as it was only the beginning of what the data revealed. As scientists continued analyzing Voyager 1's transmissions, they found that the interstellar medium was not behaving the way theoretical models predicted. The density of plasma in interstellar space was fluctuating, not randomly, not chaotically, in structured patterns that persisted over distances measured in astronomical units, each. Astronomical unit being the distance from the Earth to the Sun, interstellar turbulence, density waves, variations in the magnetic field threading through this region of space that were stronger than any prior model had suggested they should be. The universe beyond the edge of our solar system was more active, more structured, and more complex than anyone had calculated. The comfortable old picture of interstellar space as a quiet, featureless void was being dismantled, one data packet at a time, by an aging spacecraft running on the power equivalent of 3 household light bulbs. What most people are not seeing in the mainstream coverage of this mission is the deeper implication of what Voyager's data means for our understanding of the heliosphere itself, the protective magnetic bubble that our sun generates and that surrounds every planet in our solar system, including Earth. For decades, scientists assumed the heliosphere was a relatively stable, well-defined structure. Voyager 1's measurements of the interstellar medium surrounding it are revealing that this assumption was too simple. The magnetic field in the very local interstellar medium, the region just outside the heliopause, is stronger and more organized than models predicted. This means the external pressure being exerted on the heliosphere from interstellar space is different from what we calculated, which means our models of how the heliosphere protects Earth from galactic cosmic radiation, high-energy particles streaming in from the wider galaxy, may need fundamental revision. Think about what that means for us here on Earth. The heliosphere is not just an abstract feature of solar physics. It is, in a very real sense, a shield. Galactic cosmic rays, particles accelerated to extreme energies by supernovae and other violent events elsewhere in the galaxy, constantly bombard the boundaries of our solar system. The heliosphere deflects and attenuates a significant fraction of those particles before they can reach Earth. The question of exactly how effective that shield is and how it responds to variations in the interstellar environment surrounding it is not a question with purely academic consequences. It is a question with direct implications for understanding the radiation environment that life on Earth has existed within throughout its evolutionary history. And Voyager 1's data is telling us that we do not fully understand that shield yet. Now factor in what happened in May 2025, because the story takes another turn here, one that was covered in technical press releases, but whose full significance was buried under the engineering details. Voyager 1's primary roll thrusters, the small jets that control the rotation of the spacecraft to keep its antenna pointed at Earth, had been degrading for years due to residue buildup inside the thruster tubes. Without functioning roll thrusters, Voyager 1 would slowly drift in its orientation. Its antenna would point away from Earth. The data stream would go silent. The mission, all of it, every remaining instrument, every future measurement of this unprecedented region of space, would end. NASA engineers identified backup roll thrusters that had been dormant since 2004. 21 years of inactivity. They were officially classified as non-functional. The mission team had essentially written them off as dead. And this is where the story becomes something more than an engineering problem. Because one engineer, or one person on the Voyager mission team, had a different hypothesis about why those backup thrusters had failed. The accepted conclusion was that they were irreparably damaged. This engineer's conclusion was that the heaters keeping the thrusters warm enough to operate had been accidentally switched off. and that if the heaters could be switched back on before the thrusters fired automatically as a safety response, it might be possible to bring them back to life. The catch was that there was a strict and unforgiving deadline. From May 4th, 2025, the antenna in Canberra, Australia, the primary antenna in NASA's Deep Space Network responsible for sending commands to Voyager 1, would go offline for months of upgrades. If the thruster reactivation could not be completed before that date, there would be no second chance, no fallback position. The window would close, and Voyager 1 would begin its slow, silent drift toward communication blackout. On May 14th, 2025, NASA announced that the operation had succeeded. The backup thrusters, dead since 2004, written off as lost, officially classified as non-functional for over 2 decades, had been brought back to life. Todd Barber, the mission's propulsion lead at the Jet Propulsion Laboratory, used a specific word to describe what happened. He called it a miracle save, and he did not use that word casually. These thrusters were considered dead, he said, and that was a legitimate conclusion. It's just that one of our engineers had this insight that maybe there was this other possible cause, and it was fixable. One engineer, one insight, 22 hours each way across 14 billion miles of vacuum. And the mission survived. But why does that matter beyond the engineering achievement? It matters because of what Voyager 1 is now able to continue doing. With functioning thrusters maintaining its orientation, the spacecraft can keep its antenna pointed at Earth, which means the data keeps coming, which means the scientific instruments, the plasma wave system, the magnetometer, the low-energy charged particle detector, the cosmic ray subsystem, continue their measurements of a region of space that nothing else in human history has ever measured. Every day that Voyager 1. What keeps transmitting is a day of irreplaceable data from an environment that cannot be replicated, simulated, or approximated from Earth. There is no telescope that can observe interstellar plasma density variations on astronomical unit scales from a distance. There is no computer model that does not ultimately depend on the direct measurements that only Voyager 1 can provide. Keeping this spacecraft alive is not sentimentality, it is science at its most consequential. Here is what the real story is. The data arriving from Voyager 1 is not simply adding details to a picture we already understood. It is revealing that the picture was wrong in fundamental ways. The interstellar medium is not empty. It hums. It fluctuates. It carries structure and turbulence and magnetic organization that our models did not predict. The boundary between our solar system and interstellar space, the heliopause, is not a clean, stable line. It is a dynamic pressure, sensitive frontier that responds to both the internal activity of our sun and the external conditions of the interstellar environment. And those external conditions, according to Voyager 1's measurements, are more variable and more complex than any theory prepared us for. Consider the cosmic ray findings specifically. Scientists analyzing Voyager 1's measurements of low-energy cosmic rays, particles streaming in from outside the solar system, found patterns in the data that challenged existing models of where those cosmic rays originate and how they travel through the galaxy. The data suggests that the nearest significant sources of the cosmic rays that reach our solar system are located at distances greater than 150 to 200 parsecs from the Sun. 1 parsec is approximately 3.26 light years. What that means in practical terms is that the cosmic rays washing over our heliosphere are not coming from nearby stellar explosions or nearby galactic events. They are arriving from much further away, which means they have been traveling for vastly longer periods of time, which means the relationship between cosmic ray flux and local stellar activity is not what the models predicted, and which means our understanding of the radiation environment surrounding Earth throughout its entire geological and biological history needs to be reconsidered. This is not a small revision. Scientists understand the connection between cosmic ray flux and Earth's climate, Earth's cloud formation, Earth's mutation rates, and Earth's long-term biological evolution. The cosmic ray environment is woven into the deepest history of life on this planet, and Voyager 1 is telling us we have been measuring that environment without fully understanding its sources. According to informed sources in the astrophysics community, these findings are prompting a serious reevaluation of propagation models that have been standard for decades. The data is not yet enough to overturn the models entirely, but it is enough to reveal their edges, to show where the assumptions run out and the unknowns begin. Then there are the magnetic field anomalies. Voyager 1's magnetometer has recorded magnetic field strengths in the very local interstellar medium that are consistently stronger than theoretical predictions. In some periods, the field has been described in published research as showing a magnetic hump, a structured elevation in field strength followed by slowly varying, unusually strong magnetic readings persisting for years. After encountering this feature, the magnetic field's angular orientation has been declining, in a pattern that is nearly linear, which is itself a structured and organized behavior, rather than the random variation one might expect in a supposedly empty region of space. Something in the interstellar medium near the heliopause is generating or sustaining organized magnetic structure, and nobody yet has a complete explanation for what that something is. One scientific theory invokes the concept of the heliocliffe, a hypothesized sharp transition zone at the very edge of the heliosphere where conditions change rapidly and dramatically. Another theory points to the possibility that Voyager 1 is measuring the effects of ancient interstellar shock waves, pressure fronts from supernovae that occurred thousands or even millions of years ago, still propagating through the interstellar medium like the ripples from a stone thrown into an impossibly large pond. The mathematics of such ancient shocks are consistent with some of the structures Voyager 1 has detected. But consistent with is not the same as explaining. There's a difference between a theory that fits the data and a theory that accounts for the data completely. And right now, no single theory accounts for everything Voyager 1 is measuring. What most people are not seeing is the significance of the fact that we have exactly one data source for all of this. One spacecraft, one set of aging instruments, one thread of telemetry arriving across a distance that light itself needs more than 22 hours to cross. There is no second Voyager positioned nearby to cross-check the readings. There is no backup probe deployed to verify the magnetic anomalies, or confirm the plasma hum, or triangulate the cosmic ray patterns. There is only Voyager 1, and the extraordinary, irreplaceable measurements it continues to produce every day. It remains operational. When this mission ends, and it will end as the spacecraft's nuclear power source slowly decays and its instruments go dark one by one, we will not be able to replace what it sees. Not with any technology that exists today, not with anything currently planned. The next interstellar probe is a concept, not a funded mission. The timeline for reaching the heliopause again with a new spacecraft using currently available propulsion technology is measured in decades, which means every additional day of Voyager 1's operation is not just scientifically valuable, it is scientifically irreplaceable. And yet, despite all of this, despite the corrupted memory chips and the dead thrusters brought back to life and the continuous plasma hum and the magnetic anomalies and the cosmic ray findings that challenge propagation models used for 50 years, the mainstream conversation about Voyager 1 tends to focus on the heartwarming narrative of the little spacecraft that could, the nostalgic story of humanity's farthest ambassador, the golden record attached to its side, carrying greetings in multiple languages for any civilization that might someday find it. Those stories are not wrong. They are real and they carry genuine emotional weight. But they are not the whole story. The real story is in the data. And the data is telling us something that the nostalgic framing obscures. We are less certain about the universe beyond our solar system than we thought we were. And Voyager 1 is the only instrument we have capable of correcting that uncertainty. The scientific community is not panicking. Astrophysicists are not losing sleep over Voyager 1's data in the way that headlines sometimes suggest. But they are paying close attention. They are revising models. They are publishing papers that acknowledge tensions between theory and measurement. They are having conversations about what a future interstellar probe would need to carry and where it would need to go to resolve the questions that Voyager 1's findings have raised. And those conversations are characterized by a particular quality of intellectual discomfort that anyone who has spent time in serious scientific research will recognize immediately. It is the discomfort that comes not from confusion, but from the specific sensation of realizing that a framework you trusted was incomplete, that the map you were navigating by had blank spaces where you thought there were clear roads. Here is a specific example of that discomfort rendered in numbers. The interstellar magnetic field in the region Voyager 1 is currently traversing has been measured at strengths above 0.4 nanotesla. That sounds like a tiny number. It is a tiny number by any measure of magnetic field strength that humans encounter in daily life. But it is considerably stronger than the theoretical models of this region predicted. And in astrophysics, where models govern, predictions about radiation environments, particle behavior, and the dynamics of the heliosphere. A discrepancy between predicted and measured magnetic field strength is not a footnote. It is a flag. It signals that something in the model's assumptions about the structure of the interstellar medium near the heliopause was wrong. The question is not whether the models were wrong. They clearly were. The question is, how wrong? And that question cannot be answered from Earth. It can only be answered by Voyager 1, transmitting its measurements across 14 billion miles at the speed of light, one slow data packet at a time. The plasma hum itself deserves more attention than it typically receives. When Stella Koch-Ocker and her colleagues at Cornell University identified the persistent plasma wave emission in Voyager 1's data, published in the journal Nature Astronomy, they were not describing a curiosity. They were identifying a new tool, a new way of measuring the interstellar medium. Before this discovery, scientists could only measure the density of interstellar plasma, when solar shock waves propagated through the medium and caused temporary bursts of plasma. Oscillation. The steady hum that Voyager 1 detected between those bursts provided a continuous measurement capability that had never existed before. It is the difference between only being able to measure ocean depth when a wave crashes and being able to measure it continuously between waves. The difference between snapshot and continuous monitoring. And what that continuous monitoring revealed as Voyager 1 moved through interstellar space at 35,000 miles per hour was that the interstellar medium has structure on scales we did not anticipate. Density fluctuations, turbulence patterns, variations that trace the large-scale architecture of the space between stars in ways that static models simply could not capture. According to informed scientific sources, one of the most striking aspects of these measurements is their implication for what the interstellar medium will look like as our sun continues its journey through the galaxy. The sun is not stationary. It orbits the center of the Milky Way, completing one orbit approximately every 225 million years. In that time, it passes through different regions of the interstellar medium, regions with different densities, different magnetic field strengths, different levels of cosmic ray flux. The heliosphere that protects Earth changes in response to those different environments. When the sun passes through a particularly dense region of interstellar medium, the heliosphere compresses. When the external pressure decreases, the heliosphere expands. These changes have direct consequences for the radiation environment at Earth's surface, for the long-term climate, for the mutation rate of living organisms, for the evolutionary pressures acting on all life on the planet. Voyager 1's data is giving us our first direct measurements of the interstellar medium's local structure, and suggesting that it is more variable, more organized, and more dynamically complex than our models of these long-term heliospheric changes have assumed. The deeper you go into what Voyager 1 is actually measuring, the more you realize that this is not a story about one spacecraft. It is a story about the boundaries of human knowledge, specifically about where those boundaries are, and how different the reality beyond them turns out to be from what we confidently predicted. Science operates by building models and then testing them against reality. The testing is the critical part. Without it, the models become doctrine. They become the assumption behind the assumption, invisible and unquestioned. Voyager 1 is the test. It is the only instrument positioned in the only location where the most fundamental models of our solar environment can be evaluated against direct measurement. And what it is telling us is that the models were good, but not good enough. That the universe at the edge of our solar system is richer, stranger, and more textured than our equations predicted. And so, here is where we are left. A spacecraft the size of a school desk, powered by the radioactive decay of plutonium, built before the age of digital computing, is drifting through interstellar space at 35,000 miles per hour. Its thrusters, twice dead, twice resurrected by engineers whose creativity exceeded the limits of what the hardware should have been able to do, are keeping its antenna pointed at Earth. Its plasma wave system is detecting a continuous hum from the fabric of interstellar space that no theoretical model anticipated. Its magnetometer is recording magnetic field strengths that exceed predictions. Its cosmic ray instruments are mapping a radiation environment whose sources are further away and more complex than the models assumed. And the data is arriving. Slowly, patiently, 22 hours each way across the largest distance any human communication has ever crossed, in packets that scientists are still working to fully understand. What happens when the power finally runs out? What happens when the plutonium decays below the threshold required to operate even the most basic instruments? What happens when the last data packet arrives and the signal falls silent for the first time in nearly 50 years? Those questions have answers that are already written. Within the next few years, perhaps by 2030, perhaps a little beyond, Voyager 1 will go dark. The hum from interstellar space will no longer have a listener. The magnetic field variations will go unmeasured. The plasma density fluctuations will continue, but there will be nothing and no one to record them. And humanity will be left with what Voyager 1 managed to send back, a partial map of a territory that stretches to infinity in every direction, drawn by an instrument that reached its destination by accident of persistence rather than by design. The real question, the one that nobody is fully answering yet, is what we do with what Voyager 1 has revealed. The models are incomplete. The interstellar medium is stranger than we thought. The heliosphere's behavior in response to its environment is more complex than the equations described. The cosmic ray sources are further away than the propagation models assumed, and the magnetic structure of the space just beyond. Our solar system carries organized features whose origin is not yet understood. These are not minor discrepancies. They are signposts pointing toward something larger, toward a fundamental revision of how we understand the environment that our sun, our planet, and all life on Earth inhabits within the broader galaxy. The hum is still out there. The data is still arriving. And somewhere in those transmissions, those thin, faint signals crossing 14 billion miles of darkness at the speed of light, is information that will eventually force a rethinking of things we thought we understood. We just do not yet know exactly which things. We do not know exactly how deep the revision will go, and perhaps most unsettling of all, we do not know what Voyager 1 will encounter next as it pushes further into a region where no map has ever been drawn, because no traveler has ever gone before. The universe at the edge of our solar system is not what we thought it was. And the machine that told us so is still moving, still humming along with the signal it discovered, still sending home its impossible dispatches from the frontier. What it finds next may answer the questions we are asking now, or it may ask questions we are not yet prepared to hear.